This clip we're focusing on a grade B section of work from measures, where we're looking at the largest or maximum and minimum possible values that could come from something that has been rounded. It's quite easy when we're working with discrete measurements to understand, but it gets a little bit trickier when we're dealing with continuous. So if we kick off looking at discrete, the sort of things we're looking at here are things like the number of people, shoe size, money, sweets in a jar, cookies in a jar, that sort of thing, that have been rounded to the nearest 100 or 10. So for example, there were an estimated 90 trolls in the field to the nearest 10. What is the lowest possible number of trolls? What is the highest possible number of trolls? So if it's been rounded to the nearest 10, then that means that there are numbers smaller than 90 that it could have been that would round up to 90, and there are a number of trolls higher or larger than 90 that it could have been that would have been rounded down. Now when things are rounded to the nearest, a way to think about that is if it's to the nearest 10, then that means that if you divide that by 2, so we could say that there are 90 plus or minus 5 trolls. So 5 above or 5 below. So 85 is the minimum, because 85 rounds up to 90. Now, because we are talking here about whole numbers, trolls, 95 would definitely round up to 100. So the minimum number of trolls is 94. Sorry, the maximum number of trolls is 94. So we're going 5 below, and in this discrete case, even though I've said they're plus or minus 5, that will make more sense when we come to continuous. 94 is the highest number of trolls in the field that would round to 90. So the lowest would be 85 and the highest would be 94. Now money is also something that's often rounded to the nearest pound. So £10 is rounded to the nearest £1. What is the lowest possible value of the coins? Well, again, if we think of this idea of taking the rounding value and halving it, so we'd be doing £10 to the nearest pound. So we do £1 divided by 2 is 0.5, so 50p. So it's going to be £1, £10 plus or minus 50p. So the minus 50p would be £9.50. So the smallest value would be £9.50, because £9.50 will definitely round up. If we add 50p to that, we'd get £10.50. But because we've got particular coins in our currency, we know that 49 pence exists. So what would actually be the largest value that would round down to 10 would be £10.49, because £10.50 would round up. So that's if we're working with discrete measurements and we know there is an actual whole number as a maximum value. It gets a bit trickier when we're measuring, when we're working with continuous, because when we're measuring something, we are taking a decision as to how accurate we want to measure it, whether we're measuring to a millimeter, a centimeter, a meter, or a kilogram, a gram. It depends on the level of accuracy we need and the level of accuracy of our measuring equipment. So this example here, we're measuring the length of a floor tile to the nearest centimeter. So to the nearest centimeter, to round up to 20, that will have a clear cut-off of 19.5 centimetres. Now if it's to the nearest centimetre, then 1 centimetre divided by 2 equals 0.5. So we're taking that nearest rounding, halving it to work out what is going to be either side. So if it's 20 centimetres, then the upper and lower bounds will be 20 less 0.5 below, which is the 19.5 there. Or if we look at this upper one, then that would be 20 plus 0.5, which is 20.5 centimetres. Now this is where the confusion kicks in. We know that anything 19.5 rounds up to 20 to the nearest centimetre, but we also know that 20.5 would also round up to 21. So it gets a little bit confusing when working with continuous data if we are saying 20.5 is the upper bound. But we do that because otherwise we end up talking about 20.4 rounding down, yes it does, and 20.5 rounding up. But 20.49 would also round down, but is higher, is a larger value than 20.4. That's larger again. So this is where we're looking at the continuous measure of it. It depends how accurate we are measuring something. So 20.49, the actual upper bound that we could write and would be acceptable is 20.49 recurring with a dot above it, so 20.4999999. But for the sake of the maths that we'll be doing in the examples that we're going to work through, we take the upper bound to be 20.5, it won't exceed that, and the lower bound to be 19.5. So if it's the nearest 1 centimetre, you do 1 divided by 2 is a half, so the bounds are going to be 20 plus 0.5 or 20 minus 0.5. That's described in the next slide, where we can see the two extremes together. This floor tile, if it measures as 20 centimetres to the nearest centimetre, could be as small as 19.5, but it could be as large as anything up to 20.5. And it's these differences in measurement that the GCSE questions challenge us to understand. This hasn't printed very well, but it's clear on the PowerPoint if you download the PowerPoint. So we got Jake Dödelberger caught a large trout. He weighed it and found it to be 14 kilograms to the nearest kilogram. So nearest kilogram, 1 kilogram divided by 2 equals 0.5 kilograms. So my bounds are 14 plus or minus 0.5. So the least possible weight would be 14 minus 0.5. Which is 13.5. And the largest will be the upper bound, which is 14 plus 0.5, which is 14.5 kilograms. So anything between there rounds to 14. He wants to sell the trout to a fishmonger. What weight would Jake like to use? Well, they're normally sold so much, £10.84 to the kilogram. So he would want to use the heaviest weight. So he would want 14.5. The fishmonger would want to use the lightest weight, which is 13.5. Okay, so let's take a look at some exam questions. A rectangular piece of cardboard measures 14 centimetres by 9 centimetres, each measurement being correct to the nearest centimetre. So the boundaries, the error boundaries, are going to be plus or minus 0.5. One centimetre divided by 2, so we'll have plus or minus 0.5 centimetres. So the width is going to be 14 plus or minus 0.5, and so the height will be 9 plus or minus 0.5. So A, the least possible values of the width. So the least width will be 9 minus 0.5, and the least length will be 14 minus 0.5, which is 13.5 centimeters. The greatest values so the greatest width will be 9 plus 0.5, and the greatest length will be 14 plus. Part C, write down the least and greatest possible values of the perimeter of the rectangle. So if you want the perimeter of that rectangle to be as large as possible, then you're going to want the greatest length and the greatest width. Max values. Okay, so for the greatest possible perimeter, I want to add the largest side to the largest width to the largest side to the largest width. So that would be 2 lots of 14.5 plus 2 lots of 9.5. So 14.5 plus 14.5 plus 9.5, so 48 centimeters would give us the maximum perimeter, because if we were using the smaller values we would get a smaller sum around that rectangle. So for the largest perimeter we need that. For smallest perimeter we'd work with minimum values. So for the smallest perimeter we need the minimum values, which would be 13.5, 8.5, There again. So 44 centimeters. So there's quite a difference between the minimum and maximum perimeters for that rectangle. So if that was a rectangular cake, for example, and you were needing to go and buy some ribbon to place around the side of it, you need to consider these minimum and maximum values in order to make sure that the ribbon that you buy is long enough. And then for part D, least and greatest possible values of the area. Well, again, to get a maximum value you want two large numbers to multiply together. So max area would be the two largest values. length and width. So 137.75, and the units for area would be centimetres squared, and the min area will be the two smallest values multiplied together. So 13.5 times 8.5, which is 114.75 centimetres squared. So because we've measured this rectangle to the nearest centimetre, that means that the area of it could be anything between 114.75 square centimetres, excuse me, and 137.75 square centimetres. Okay, we're still working with that same piece of card. 4 of them are placed in a row with their shorter sides joined. Calculate the least and possible values of the length of the 4 pieces of cardboard. So this will be the length. For the least length, we'd want 4 of those to be measuring their minimum value. So 4 lots of the minimum length. .54 centimetres. The maximum length will be 4 lots of max, which will be 4 lots of 14.5. .58 centimetres. And this leads us to the sort of question you might get asked in a GCSE, which would be if those were floor tiles and you were trying to fit them across a width of a room, could you guarantee they would always fit? So it would depend on what the width of the room was to see whether, if they were all at their most extreme length, their maximum length, whether that would fit in. I will see an example like that in a short while. F. 2 pieces of cardboard are placed as shown in the diagram. Calculate the least and greatest possible values of the length AB. So this one now requires a little bit more careful thought. What we're going to do to work out that length is subtract the width of the tile from the length of the tile. So AB will be length of tile less width of tile. Now if we want that to give us the smallest possible value, then we want to be taking a large value from a small value. So this time for min AB, so for minimum AB, we want the minimum length, the smallest length, and we want to take a big number away from that, so we want the max width. So minimum length, take away maximum width, will make that distance as small as possible. So the minimum length was 13.5. The maximum width was 9.5. So we do 13.5, take away 9.5 is 4 centimeters. So the narrowest that gap can be is 4. If we want that gap to be as large as possible, so for max AB, we want the width, the number that we're subtracting from, to be as large as possible. So we want max length, and we want to take a small number away from it. So we want that width there to be as narrow as possible. So we want the maximum length less the minimum width, which would be 14.5 is the largest that length can be, less 8.5, which is the smallest that could be, and that will create the largest gap for AB. So that gap could be as small as 4 centimeters, but as large as 6 centimeters, depending on where those values lie between those extremes. So you need to think, it's not always maximum maximum or minimum minimum. Sometimes it's a combination of the two. Question 2. A rectangular piece of cardboard have lengths 28 centimeters and widths 16 centimeters, each measurement correct to the nearest centimeter. So we're measuring to the centimeter again, so the error boundaries are going to be half of a centimeter. So we take the nearest centimetre, so 1 centimetre divided by 2 is a half. So there's going to be plus or minus half a centimetre either side of our rounded values. So the minimum length will be 28 minus 0.5. And the minimum width will be 16 less 0.5. I've done the least possible values, so they're not asking for the greatest, so that's all we need to do there. 4 of these pieces of cardboard are placed in a row with their shorter sides joined. Calculate the least and greatest possible values of the length of the 4 pieces. So we've got our placed in a row like that. This will be the length. So the least length will be 4 lots of 27.5. The minimum length of each rectangle. (110 centimeters), and the maximum length would be 4 lots of the greatest that could possibly be, which would be 28 plus the error boundary, 28.5. 114 centimeters. 2 pieces of cardboard are placed as shown in the diagram. Calculate the least and greatest possible values of the length of AB. Similar to the previous question, yeah? So for the greatest length of AB, max AB will be the maximum length minus that as small as possible min width. So max length will be 28 plus a half. Min width will be 16 minus a half. (13 centimeters). And then the minimum distance AB, you'd want the width to be as small as possible, the length to be as small as possible. So you have min length, and you'd want this here to be as wide as possible. So the minimum length, 28 less 0.5. The maximum width, 16 plus 0.5. So 11 centimetres. So that gap AB could vary from anything between 11 and 13 centimetres wide. Question 3. The length of the desk is measured as 180 centimetres, correct to the nearest centimetre. So our error bound is going to be plus or minus a half centimetre. Greatest and least values of the length. So the least min length will be 180 less 0.5 is 179.5 centimeters, and the max length will be 180 plus 0.5 centimeters. 3 of these desks are laid end to end along their lengths. What is the least value that the total length of the 3 desks will be? Minimum length will be 3, and you'd want 3 of the shortest possible desks, which would be 179.5. So 3 lots of 179.5, 538.5 centimeters. The distance between the 2 walls is measured as 3 meters, correct to the nearest centimeter. Write down in centimeters the least and greatest values of the distance between the 2 walls. So first of all, 3 meters you need to change into centimeters. You need to know that there's 100 centimeters in a meter, so 3 meters is 300 centimeters. It's the nearest centimeter, so the error bounds are going to be plus or minus 0.5. Write down in centimeters the least and greatest values of the distance between the 2 walls. So min dist, so the minimum distance will be 300 minus 0.5, which is 299.5 centimeters, and the max distance will be 300 plus 0.5, which is 300.5 centimeters. One desk is placed lengthwise between the 2 walls and in contact with the left-hand wall as shown in the diagram. What is the greatest possible length of the gap between the desk and the right-hand wall? So for that gap to be as large as possible, I want the distance between the 2 walls to be a big number, and I want the desk to be as small as possible. So I want max distance here, and the max distance is 300.5 centimeters, and I want this to be the min length of the desk, and the minimum length of the desk is 179.5 centimeters. So if that distance is as big as possible and I take the smallest possible distance away from it, I have the maximum gap. So max gap will be 300.5 less 179.5. So 121 centimeters is the largest that gas gap could possibly be. Question 4. A lump of plasticine has a mass of 500 grams correct to the nearest 10 grams. A piece of the plasticine is removed and found to have a mass of 310 grams correct to the nearest 10 grams. Find the greatest possible value of the mass of the remaining lump of plasticine. So this time we measure into the nearest 10 grams, so the error bounds will be 10 divided by 2 is plus or minus 5 grams. So the maximum mass of the plasticine will be 500 plus that 5 gram error bound is 505 grams. No, that's 5,005 grams. So 505 grams. Now what we're doing here is we want to find out what the greatest possible value of what's left is. So the greatest possible value of what's left is if the original lump is at its maximum value and the piece that's been removed is at its minimum value. So I want the minimum mass of removed piece, which will be 310 less 5 grams. So the maximum value of remaining the max mass remaining will be the largest original lump minus the smallest removed lump. Which is going to be 200 grams. So that's as heavy as the remaining mass, remaining plasticine could be. A rectangle's measurement are given as 30 centimeters by 20 to the nearest centimeter. Find the least possible length of the perimeter of the rectangle. So if they're measured correct to the nearest centimeter, the error bounds will be 1 centimeter divided by 2 plus or minus half a centimeter. For the minimum perimeter, I want each of those to be as small as possible. I want min length and min width. So min width is going to be 20 less 0.5, which is 19.5. 2 of those, and the minimum length is going to be 29.5. So 19.5 so I've gone wrong there. See, I'm going to multiply, do it again. 19.5 so 98 centimeters will be the minimum perimeter. So there we go, there's some practice at using error bounds to find upper and lower limits when taking measurements.